Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It is our first lesson on the 7th topic of Form 3 work, which is called Electrostatics 2. As usual, let me comment by giving you the quote of the day, which states that your mind is like an umbrella such that it is most useful when open. We shall discuss that quote at the end of our class today. So today we are looking at Electrostatics 2, which is just a continuation of Electrostatics 1. So to understand Electrostatics 2 better, I will advise you to review our lessons on Electrostatics 1, which was topic 9 of Form 1 work in this particular channel. So that is under Electrostatics 1, we did say that the word electrostatics originates from two words. That is an electro, which is just the short form of an electron. Remember, an electron is just one of the two types of charges. Remember, we had the protons and the electrons, whereby the electrons were the negative charges. Then static simply means stationary or not moving. Therefore, we did say that the word electrostatic simply means the study of static charges, the study of static charges. In the same topic, that is under Electrostatics 1, we also said that the units that we use to measure charges are simply what we call the coulomb. Then we said that coulomb is simply derived, or the name of the units of charge, that is the coulomb, was simply derived from the name of that is an engineer and a physicist who was from France by the name Charles Augustin de Coulomb. So because of the last name Coulomb, he was given, that is, his last name was taken to be the units of charge, which is simply the coulomb. So we want to look at the forces between charged bodies. So to study that, let's consider these particular electroscopes here. So I have my electroscope here, which I want to charge by induction method. Remember, also in Electrostatics 1, we did look at the two ways of charging an electroscope. We talked of conduct method and also induction method, whereby the conduct method, that is whereby you bring the charging material to be in contact with your brass cap. But for this case, we are using induction method, whereby we'll be bringing our charging material close to but not in contact with our brass cap. So this is our polythene rod, or the negatively charged rod. So we are just bringing it close to but not in contact with our brass cap. Remember, we also said that the brass cap is initially neutral. Then we said that neutral simply means that the number of positive and negative charges are at balance. For example, in this particular brass cap, initially, before we began the experiment, we had 1, 2, 3, 4 protons. Then it means we also had 4 electrons. That is, the number of positive and negative charges were at balance. That is what we mean by a material being neutral. However, when you bring a polythene rod close to but not in contact with the brass cap, because it has 2 negative charges or 2 electrons, the electrons will actually repel the 2 electrons on this particular brass cap. So the 2 electrons which were in the same position with these 2 positive charges, they will be repelled downwards. So one of the electrons goes to the metal rod, the other one goes to the leaf. So because the metal rod and now the leaf are they have like charges, and we know that from the law of charges, we did say that like charges will always repel each other. So the electron and this particular electron will repel each other. Therefore, we shall expect to see a divergence in the leaf. So the leaf is going to diverge because the metal rod and the leaf are simply negatively charged. Therefore, they are repelling each other. However, when you increase the number of polythene rods, or when you increase the number of charges on these particular materials, it is observed that if we have 4 positive charges, 4 negative charges here, or 4 electrons, they are going to repel 4 electrons from this particular brass cap. So when 4 electrons are repelled downward, so we shall have 1, 2, 3, 4 electrons which have been repelled. So we have 2 electrons which will go to our metal rod, then the 2 electrons will go to the gold leaf. So of course the metal rod and the leaf will repel each other because they are negatively charged, or they have like charges. So because here we are talking of 1, 2, 3, 4 charges, we shall expect the divergence of the leaf to be greater. So we are going to have a greater divergence in that particular leaf. And remember, the divergence is due to electrostatic forces. That is the repulsive electrostatic force. So that simply shows you that the more the amount of charges, the more the repulsion, or the more the amount of charges, the more the electrostatic force. And the fewer the amount of charges, the smaller, or the smaller the electrostatic force. So that simply shows you that the electrostatic force is directly proportional to the quantity of charge that is on a material, such that if a material has fewer charges, the divergence will be less, showing that the electrostatic force is also less. But if the charges on the material are more, then we also expect a larger divergence, showing that the electrostatic force, that is the repulsive electrostatic force produced on this particular leaf, will be very, very large. So we have the two factors which will affect the forces between charged materials. So one of the factor is just the quantity or the amount of charge. So the more the amount of charge, the more the electrostatic force that will be produced. Then the other factor affecting the force of electrostatic, or the quantity of the electrostatic force that will be produced, is the separation distance between any two charges. For example, in this particular case, we have our pith ball, two pith balls which are actually positively charged. So we are tying one on using a nylon or a silk thread on this particular material here, just a rod. Then we have another insulating handle which is also having a positively charged pith ball. So of course, positive and positive charges will always repel each other. But when you bring this particular insulating handle very close to this particular positive charge, the repulsion will actually be greater, showing you that the smaller the separation distance, the more the repulsive force. However, if you take this particular insulating handle far away from this particular charge, actually this pith ball will not be repelled. So the pith ball will remain in its position, showing that the electrostatic force will be very, very small. So the smaller the separation distance, the greater the repulsive force, or the greater the electrostatic force. Remember, we said that electrostatic force simply refers to the force of attraction or repulsion between static charges. So we have seen that the smaller the separation distance between the charges, the greater the electrostatic force, and the larger the separation distance between the charges, then of course the smaller the electrostatic force. Therefore, we can conclude that the electrostatic force is inversely proportional to the separation distance, such that the smaller the separation distance, the greater the electrostatic force. Next, we look at what we call electric field patterns. So remember, to understand this better, you can just relate with what we were calling the magnetic field patterns. That is in the first lesson, or the first topic of that is magnetism, which was our first topic under Form 2 work. So in that particular topic, we did say that magnetic field refers to the region around a bar magnet where the force of attraction or repulsion is strongly felt. Now, in this case, we are talking of electric field. We are not now talking of magnetic field. So for electric field, we'll start by defining what we mean by electric field. So it is just a region around a charged body where the force of attraction or repulsion is felt. Yeah, remember, when you bring two like charges together, they will repel each other. But when you bring unlike charges closer to each other, they are going to attract each other. That's why you are talking of either attraction or repulsive force is felt. So there is a region, for example, for this particular charge of mine here, maybe when you bring another positively charged rod, if you place it somewhere here, it will not have any effect on this particular body. However, if you bring a positively or a negatively charged body closer to this particular charge, you are going to experience the forces of attraction or repulsion. So the region or the area around a charged body where the force of attraction or repulsion is felt, that is what we call the electric field. So electric field will always be very closer to that particular charge. So such that when you move away from the charge, then the region does not become an electric field because the force of attraction or repulsion won't be felt. Then next we look at electric field. So electric field is usually represented by what we call electric field lines. Here you can just relate them to magnetic field lines. So electric field lines are defined as the lines along which the electrostatic forces act. So if you're asked to define what we mean by field lines, you simply say that is electric field line. You simply say that are lines along which the electrostatic forces act. Then electric fields have the following properties. So one is that electric field lines are directed away from the positive charges and towards the negative charges. As you can see, the positive charges, you can relate it to the North Pole, that is under magnetism. We saw that the North Pole, the magnetic field were moving from the North Pole. Now for the charges, the electric field will always be moving from the positive charge or from the positive terminal. So they will originate from the positive charge. That's why our arrows are pointing away from this particular charge. Then those particular electric field lines will always enter. They will always move towards the negative charge. So you can see for this case, the arrows are entering this particular charge, but for the positive charge, the arrows are moving away, showing that the lines of force will always move or originate from the positive terminal, and they always enter the negative charge or the negative terminal. Next, we look at the second property of magnetic field lines. That is the second property of magnetic field. So is that unlike charges attract while like charges repel. Remember, the same statement is also the law of electrostatic charges, that like charges will always attract, but like charges will always repel each other. Remember, when we talk of unlike charges, we mean that charges that have different properties. For example, one of the charge being positively charged while the other one being negatively charged. So these two charges are unlike. That is, they are not of the same like, or they are different. Then when we talk of like charges, like simply means that they have similar properties or they are identical, such that when you talk of two like charges, you are talking of a positive and a positive charge, or you are also talking of a negative and a negative charge. So they have similar properties, therefore they are said to be like charges. Then we look at the field patterns around charged bodies which are closer together. So let's start with the field pattern along a positively charged a charged body and a negatively charged body. So from the law of electrostatic charges, we have just said that like charges will always attract while unlike, that is, unlike charges will always attract while like charges will always repel each other. Then you have also seen that the electric field lines will always move from the positive terminal or the positive charge, and they always enter the negative charge. So when you bring a positive charge and a negative charge close to each other, the charges will always, the electric field lines will always originate from the positive charge. So you can see the arrow is moving from the positive charge and they enter the negative charge. So you can see the arrows are moving away from the positive charge, and our arrows are actually entering the negative charge, obeying the first property of electric field. So the key thing here is just the direction of the electric fields. Then the other thing you have to be careful is that the charges should not intersect each other, because they usually repel each other. Then B, we look at positive charges or like charges which are closer to one another. So of course, positive and positive charges, those are like charges, so we expect repulsion. So you can see the electric fields are repelling each other, or they are moving away from each other because they have similar charges, or they are like charges. So the positive charge, we expect the field lines to originate from the positive terminal. So you can see the arrows are moving away from the positive terminal. But when you have two negative charges, we expect the fields to enter the negative charges. But because negative and negative charges are like charges, we expect repulsion. So you can see the fields are actually repelling each other, although they are entering the negative charge. Then next, we look at the field patterns for different electrodes. So remember, we should have the positive and the negative electrodes. It's just like the positive and the negative terminal. So first of all, we look at the charged positive electrodes. So when you have two positively charged electrodes, such as this one, which is positively charged, and the other one is positively charged, we expect repulsion in between them. So of course, the electric fields will always move from the positive charge or from the positive electrode. So that's why the arrows are moving away. But because this is positive, this is also positive, they repel each other. So they can never attract each other. Instead, they are repelling each other. Then also remember that the region in between here, whereby all the fields are repelling each other, this one we call it a neutral point. And the electric field at this particular point is 0, or there is no electric field at the neutral point. Then when you have charged negative electrodes, so negative and negative, of course those are also like charges, so we expect repulsion. So the charges will be, the electric fields are repelling each other sideways, and of course they never intersect. Then also the region in between is neutral, that is the field at this particular point is actually zero. The electric field in between is actually zero because the charges are repelling each other. Then also the other thing to be keen about, for the negative charges, the fields have to enter. They enter the negative charges, but they originate from the positive charges. You can see for positive charges, the arrows are pointing away from the positive charge, but for negative electrodes, the charges are moving towards, or they are pointing towards the that is the negative electrodes. The next we look at the positive point and negative electrodes. So of course the charge will move from the positive charge, so the arrows will be that way, moving from the positive charge towards the negative charge, as we saw in the properties. Then when you have the negative point and positive electrode, the charges will always move from the positive terminal towards the negative terminal, as shown in this particular case. Then the charges should move in such a way that they don't intersect each other, because if these ones are originating from the positive terminal, it means this one is positively charged, this one is also positively charged. So because they are all positively charged, they will repel each other. That is why they can never intersect each other. Lastly, we look at the electric field lines. The properties of the electric field lines. One is that they are always directed away from the positive terminal, or the positive charge, and towards the negative charge. That is, as we saw here, they move from the positive towards the negative. Then they do not cross one another. Yeah, they repel each other sideways. So the reason why they do not cross each other is because they usually repel each other sideways, because they have similar charges, or they have like charges. So because they repel each other, that's why they will never intersect each other. Just for example here, the positive charge is starting from the positive electrode. So this one is positively charged, this one is also positively charged. So because they are positively charged, they repel each other sideways. That's why they do not intersect or cross one another. Then the last property of the electric field lines is that they are parallel at uniform fields. So uniform field is such as the one here, that is at point X. So this is what we mean by a uniform field, represented by just parallel lines. Then they are widely spaced at field lines. They are widely spaced at weak field lines. For example, at point Y, you can see the fields are further away from each other. So when they are widely spaced, it means the electric field is very, very weak. Then they are closely arranged or closely packed at very stronger fields. For example, at point Z, you can see the field lines are closer to one another. So it means the electric field in this particular case is stronger at point Z, followed by, then it is the weakest at point Y. So the electric field is weak at point Y, then it is somehow stronger at point X, then it is strongest at point Z. So the closer the field lines, the greater the electric force or the electric field. But the wider the field lines, the weaker the electric field, just as we saw in magnetic fields. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that your mind is like an umbrella, such that it's most useful when open. So the quote is showing us the analogy between our mind and an umbrella. Recall that for you to use an umbrella to protect yourself against heavy rainfall, you must first of all open it. Yeah, you have to open the umbrella in order for it to protect you against the water droplets from the rain. Similarly, in order for you to use your mind to solve daily problems, you must first of all keep it open to accept new ideas and new techniques and new dimensions of dealing with that particular problem. Yeah, we need to have a mind that is not rigid, that is open to new ideas in order for us to solve problems in life. So we should therefore not be rigid in our thinking. Instead, we should be flexible in such a way that we can accept to be corrected by others and accept new ideas and new ways of working out things. And lastly, remember that we cannot solve our problems with the same thinking we used when we created them. So this amazing quote is courtesy of a great German physicist by the name Albert Einstein, who made great contributions to the discovery of quantum physics and the photoelectric effect. So until next time, this is Kind Tuition Academy. If you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. Of course, if you know anyone that you honestly think could benefit from this content, kindly refer them to Kind Tuition Academy. Until next time, this is Kind Tuition Academy.